Hey guys, good afternoon. Welcome to revision session of week 1 to 4 for quiz 1 in MLF. A quick check. Am I audible?
Yeah,
The screen is visible?
yes.
sir.
Okay.
Louder, I think.
Can you increase your system volume once?
It's at the highest.
Okay. So I'm not still audible, right?
Absolutely audible, but a little low.
Okay, so I'll check system settings. Mine is also at full, so I don't know. So it's manageable or
Go ahead, Matt.
Yeah, it's manageable, I think.
okay. Okay, so shall we start with the revision session?
Yes.
Okay. So first 4 weeks of MLF are relatively easier. That's my perception, and I think you people will also agree. So quiz one comprises of all these 4 weeks. So first week basically introduces you to the different terms, terminologies, concepts of ML without getting into too much of details. So first thing that you learn is what is ML, then what are different tasks, then why, and when you use ML, all those things. Okay, so I think we need not go into definitions and all. You people can check Hari sir's videos for that, and it's anyways easy. So ML is what you make a machine learn by providing outputs in general in case of supervised learning or by um, uh, so basically, whenever there is a situation where rules of the game are not predefined, there we use machine learning. Okay, and there are different advantages of using machine learning. Like it for traditional things, we use programming approach, which doesn't work for few things like handwritten digit recognition, or maybe image recognition, or natural language processing tasks. All those things have to be done using machine learning, since they cannot be done using traditional programming approaches. So the basic definition and use, all these things you can see from the initial lectures. So and the applications also. So we will move to the important part then, data. Okay, so in case of machine learning, data is the most important thing, right? If there is no data, there is no model. Or if you put garbage into a system, then you will get output also garbage. So data quality, data integrity, all those things should be as high as possible. So this is the first most fundamental requirement of machine learning. So basically what we do when we get data, okay, so generally it is in raw form, in some unstructured, unordered form. So what we do to build a machine learning model, we give different terminologies to the characteristics of this particular data. So what we do, we usually present the whole data set, dividing it into different records and form a matrix, which looks something like this. So all the columns of this matrix are called features or attributes. So these features or attributes basically tell you different characteristics related to a particular record. So for instance, if you want to calculate, suppose uh, uh, revenue of a company, okay, so there can be different features associated with it, like sales, discount, then advertisement, then cost of the component. All these things will become features, and they will come along the columns. So for every data or every unique record, you will start filling up the column. So these are the features of that particular data set. And rows represent a complete record or a single data point among the data set. Okay. So this, for instance, if you see this particular matrix, which consists of feature 1, feature 2, feature 3, and label, there you will find this A, B, C. This together, A, B, C, and alpha, this together forms a record or a particular data point. And this ADG, BEH, CFI are different attributes related to 3 different data points or records. Okay, so I think this much is clear with all of you. Any doubt in this? Okay, so I should move ahead maybe. So after data, the next thing which comes into picture is model. So what basically model? Model is nothing but a arbitration of reality. Okay, so and for that matter, no model can be perfect or no model is 100%. And suppose you built a 100% accurate model, I think that will be a utopia. Okay, so whenever you form a model, you basically you are trying to relate the features of a particular record to the target variable or the desired output. So in this case, the above example where ABC was a record, ABC alpha was a record, DEF beta was a record, GHI gamma was a record. There, this model will be formed using this A, B, C, D, E, F, G, H, I, and it will relate to alpha, beta, gamma. Okay, so our desired output is alpha, beta, gamma for given feature 1, feature 2, feature 3 values. Okay, so that is how you build a model. Now, model can be of different types. So, and that can be formed using different ML algorithms. Okay, so basically, you should keep in mind that model just is an arbitration of reality. It is not actually the reality. Reality has many things which cannot be accounted for, or we do not have any way of accounting that in a given model. So basically, we are trying to get closer to reality by forming a model for simplification purposes. Okay. Next thing is there are different types of ML algorithms like supervised algorithm and unsupervised algorithm. There is another algorithm called semi-supervised, which is out of scope of this course. So supervised and unsupervised algorithms are something that we will subsequently study in our set of ML courses. So first thing first, supervised approach. So whenever there is a data set in which we know the target variable or the values of the target variables are predefined. Okay, so such a set will be called supervised. So basically, our data set is supervising us for the task. Therefore, it is called supervised data set, or therefore, the learning used in those cases will be supervised learning approach. Next is unsupervised. So, in case of unsupervised, what will happen? Your data set will not have any particular target values, and you have to come up with some logical target, or you may have to find the similarity between different data points, or you have to cluster a particular data set into one group, and you have to find the topics out of a whole lot of words given to you. All those situations are come under unsupervised learning approach. So in supervised learning approach, now we have two set of rules or models that we use, which are regression and classification. So any doubt till now?
No, sir.
Okay, so in case of see, there are two kinds of supervised learning approaches. These are regression and classification. So the basic difference is the target that you are finding out. So if your target variable or label present in the data set is continuous, okay, or a real number, then you go for regression approach. And if it is a discrete value or a discrete class combination, then you go for classification approach. Okay, so this is the basic difference between regression and classification. So you can by normal logic or mathematics that we learn, you can say regression is nothing but curve fitting and classification is nothing but clustering or forming groups. Okay, so in case of regression, in first week I have seen some formulae like loss. So the loss formula which you see over here, 1 by n summation of fxi minus y whole square is mean squared error. Okay, so basically you are finding out the model that you form gives certain output, right? And the labels present in the data gives certain outputs. Now you want to find out how different they are. Okay, so regarding the kind of questions and topics, all those things, I think Anamika ma'am will answer those later on. Okay, so Pralay, maybe you can wait for some time. Let's follow the steps first. Okay, so this loss is basically you are trying to find out how deviated your output labels are with respect to the output that you get from the model, and then you divide it by n to find the mean squared error. Okay, now the model that is formed can be written as fx equal to w transpose x plus b, where this w represents different feature values. X is the X yeah, is the variables that you will want to find out, and B is the constant term. Okay. Okay. So now suppose for a given data set, your two models are given to you. Okay. Now, how will you find out whether a given model works better? So any model which produces results closer to the output variable given to you, that model by default will be considered better, right? So it means that particular model should have lost least among the given models. So in case, suppose for a given case, you have been given for a given data set, you have been given two models, F and G. And suppose the loss of F is less than loss of G, then you will say F is a better model than G. Now, similar thing happens in case of classification. So for classification, the situation becomes relatively easier. So whenever there is a correctly specified label, you call it, there is no error, okay? And whenever there is a wrongly classified label, you put a count one. So the number of counts for which you are finding that the classification is not proper divided by the total number of classification that you have performed is the loss in case of classification. Okay. Next. Now see, whenever we get a data set, we can very well divide it into three sets: test data, training data, and validation data. So basically, training data is used to train our model. So given a data set, you find out what kind of target variable you are trying to predict. So by that you, okay, Demon, you cannot hear me. Is this issue with everyone?
Sir, but volume is very low.
Yes, sir, volume is very low.
Okay, can you hear me now?
Yes.
Yeah, okay. So, any part that you missed?
Let us just get a quick, because people are complaining low volume. For me, it looks okay, maybe because my laptop volume is high.
Yeah,
Okay.
actually, I also tested the mic and speaker before joining the session. So it was working perfectly for me.
To
So
me,
anyways, it is better, right, now?
yeah, to me it looks good.
Sir.
Okay. So any part that you want me to revisit, or I can move ahead?
You can move ahead, sir.
Okay. So basically you
One
divide
moment, this, you have just told the regression and classification only. Why this density estimation and all, you are not touching it, or it is coming up later?
Yeah, it is coming up.
Okay.
Okay, so basically you form regression and classification models. Generally, density estimation is more of a data pre-processing thing that you do. Okay, so next we divide the given data set into test, training, and validation data. So training data is basically used to form the model, and it depends on the target variable that you have in the model. Okay, now generally what we do, we take 80% of the total data set and train our model, and then the rest 20% is used for testing the given data set. Now, what is the validation data? So in some cases, what we do, we validate our model, or out of all model, we do the model selection. So for that particular purpose, validation data is used. So in some cases, like where we are using cross-validation techniques, where we are forming 4 or 5 different test and training data sets, validation data is not required. But in other cases where you have a fixed training and test data, you require validation data. Okay. Next, let's move to unsupervised learning.
Sir, I have a question.
Yeah.
So if we are using 80-20 model for this testing and training, then what is validation? What data are we using for
Yeah, so
validation?
see, so what happens, you will subsequently learn about cross-validation techniques. So where what happens, you form different training and testing data out of the given data set. Okay. So in those cases, you form 4 or 5 different training and test data sets. So their validation data is not required. But if you have a fixed training data and test data, so what happens, out of the 80% that you have taken as training data, out of that you choose a particular amount as validation and keep it aside for model selection.
Okay, sir, got it.
Okay. I think that proportion is explained in some lecture by Hari sir, so you may like to revisit it. But again, it's a part of out of the whole data. You can choose a particular percent as validation, particular percent as test, and particular percent as training. So training data should be the largest. That you should keep in mind. It should be way larger than testing and validation data.
Okay, sir. Thank you.
Okay. Next is unsupervised learning. So the situations where the target variable is not given. Yeah. Any doubt, anyone?
Yeah, it is like, no, do we need to be particular about the percentages and all those things, because it will depend on the situation, no?
Yeah, it's situational.
So we need not really bother about what percentage it is and all those things, right?
Questionnaire in a sense.
Now I'm telling this test training and validation. If you are telling training data need to be 80% or about 80% or this is not an important factor as such, right?
It's important in a sense that when you are forming a model, chunk of the data should be given for training, right? So it is not like that 80% is some given rule or thumb rule. You can be 5% less or more, but in general, in practice, 80% is taken.
All right.
Okay. Next, unsupervised learning technique. So whenever we have a given data set where label is not present, we go for unsupervised. So unsupervised learning is basically used for exploratory data analysis, forming clusters or finding topics. All those things come under unsupervised learning. For instance, suppose you have been given a data set which consists of different uh, uh, articles that have been published in Washington Post. Okay, now there is no target variable as such. Now you simply want to check out how many of these given articles are sports related, then medical related, fitness related. So you are basically doing a kind of understanding of the data. So there you use unsupervised learning kind of technique. So there are clustering techniques which will be covered later in the package of machine learning courses that we have for unsupervised learning. Okay. Next, there is dimensionality reduction. So dimensionality reduction is basically a technique where you are trying to find out the important dimensions of a given data set and ignore those particular dimensions which are not that important. So basically it compresses the given data set into, for instance, you have a 3D space, then you are converting it into 2D space. So this is kind of this kind of technique is called dimensionality reduction. Okay. Goal is to reduce the dimension of the given data set from some particular dimension to a lesser dimension. That you do in case of dimensionality reduction. So the loss formula and all this you will get from the notes and the videos of Professor Hari, and you can see that. Any doubt in this?
Sir.
Yeah. No, right? Okay, then move ahead. Let's move ahead. Okay, so next is density estimation. So density estimation is used to find out the probability associated with a given data. So where that particular data lies, the probability of a data lying in different groups, that is given by density estimation. Okay, so suppose there is a situation when where we have 4 particular cases and a given data set is given to you. So you want to find out where this particular belongs. So density estimation will basically give you So it can belong to group 1, 0.2 with a probability of 0.2, group 2 with a probability of 0.4, group 3 with a probability of 0.1, and group 4 with a probability of 1 minus all other given probabilities. So that is what is density estimation. Okay. So I think this much is covered in week 1. No other topic is there. So if you have any doubt in week 1, you may ask me, and the important part related to exam and all, I think if Anamika ma'am is there.
Yeah, hi Abhinandan.
Hi ma'am. So if you have any conceptual doubt, please do ask me. Otherwise, for exam point of view, you may ask Anamika ma'am related to week 1.
Yeah, give me a moment, Abhinandan. Let me share my screen. I'm not able to share screen.
Yeah, okay. Yeah, I think ma'am, you're not a co-host.
Yeah, that's what I'm thinking. Give me a moment.
Okay, ma'am.
So the validation data is before the training data. First step is validation for selecting model. Then you have the training data, and then we have the test. Is it that way?
So see, whenever a data set is given to you, it's not first and after. You just divide it into 3 sets: training, test, and validation. So I don't know. Sequencing
Let
is
me
not there.
just add to it.
The process, as I understand, is like no, we will put the training data into this system. Then it is
first training is done. Then after training, validation is done, and then testing is done.
Yeah. So after this training, then it is likely that it might bring one model or it might bring multiple models.
Yeah.
Out of to that, we input the validation data and we select a model, and then we put it into the test data. Then we confirm that yes, this is okay.
Yeah, correct. Okay, then I think Anamika ma'am will take over from now.
Thank you.
No further doubt, right? Week 1. Yeah, okay. Anamika ma'am, thank you. Go ahead.
Yeah, sure. Thanks. Okay, so regarding this train and validation and test data, see, all the data that is given to you, you will keep some part of it. Let's say, okay, 80-20 could be one rule, 75-25 could be another, 70-30 could be another division, right? So some part of the data you will keep aside. This is the test data, and the remaining is train data. Okay, this you will not touch upon. You will sort of assume that you don't have this data. You will keep it aside. Now you have this data in order to build your model. Okay, now there are two options. One is cross validation, and the other is train and validation split. Okay, so what you can do is you can split this data. This part you will call validation data. Okay, this data will be used to choose the best model. Okay, so that's one option. This option. The other one is cross validation. So the problem in this particular approach could be, see, you use this particular data to train your model, and then this data you use for.
Ma'am, are you basically displaying something?
Oh, my screen is not visible, is it?
No, it is only that machine learning foundation
Oh, I'm
revision.
so sorry. I don't know. Let me reshare.
Yeah. Because you were telling like this.
Yeah, I'm showing something actually. No. All right, I was showing this. I'm so sorry. It's not visible. Can you see now?
Yes.
Okay.
Yes, ma'am.
Thanks for pointing out. Okay, so all right, let me just quickly tell. So let's say this is the data that is given to you, and you will keep one part of the data as test data. You'll keep it aside, assuming that you don't have access to it, because this is what you're going to use to check the performance of your model in the end. So you won't look at this data in order to build your model. So now remains this particular data, and if you want to go for, so there are two ways. One is cross validation. Second is train. I mean, you can call it validation data split. So you can follow one of these two techniques. If you go for this technique, validation data split up, you will further split this data into train and validation. Let's say again, 80-20 of this part. So this data, train data, you will use to train the model, and this validation data you will use to choose the best model. Okay, that's one way. But you know what can happen? It could be so that this split was based on a chance. Let's say you're getting some accuracy, but that was by chance. So what you do is you use whole of this data as train and validation. So that's basically a cross validation. You split this data, let's say, into 5 parts. Okay, so this is called 5-fold cross validation. So in one iteration, let's say I1, you use this data as validation, and this whole data as train. In the second iteration, you will use this data as validation and this whole data as train, and so on. I hope you get the idea. So you will have 5 iterations over the data. Now there is no, there is less possibility that the split up that you got over here was out of chance. So why? Because you're using all the data. You're using each and every data point as a validation data. You see this thing in the next one. This is I4, this is I5. So each and every data, you see this pattern. Each data point will be used for validation in some iteration or the other, and then you average out these results. So that way you get a more comprehensive, observation of which model to choose. So that's your cross validation. I hope that is clear. Now let's move on to the revision of week 2, which is based on calculus. So these are primarily the topics that are covered. So calculus is an important topic for understanding the internal workings of machine learning models. Let's say, for example, optimization is extensively used. What is machine learning? It's all about finding the best parameters, right? And how do we do that? We have an error function, and we have to find the values of parameters which minimize this error function. So this error function minimizing the value of this error function is what is called optimization. Now this error function could have some shape, right? How do we know? So what we do is we randomly start from one point, and then we move on this particular curve. The plot of this function, we move in some direction. Now, how do we choose which direction to move in? For that, we need to find the slope of that function at different points. So that's where this calculus and continuity, differentiability, and all these things are useful. So this one chapter which is on calculus is an important one. It sort of brushes up your concepts for whatever will come up later on in optimization weeks. So we prefer, by the way, we prefer that the error function should be continuous, it should be differentiable. So how do we check that? For that, we have first topic, checking continuity, and then we talk about differentiability of functions, and then we talk about linear approximation of any given higher order function. Okay, and we can also go for higher order approximations, not only linear approximation, we can go for quadratic approximations or other higher order approximations. So we'll see how we do that. And other than functions with one variable, we can also approximate functions which have more than one variables, which is called multivariate linear approximation. And finally, we talk about directional derivatives. That is finding derivative in a particular direction, not only in the direction where it is the maximum, but in some given direction. So we'll see how we do that. So going forward, continuity, I hope this is clear to everyone. We took up many examples in Solve with Instructor. So if a function is given, how do you find whether it is continuous or not? Firstly, if a general question is asked whether a function is continuous or not, you should make sure that the function is continuous at all possible points. Okay, and generally a point will be given to you, and you'll be asked to function is continuous at that particular point or not. So there are 3 things that you should first find out, and you should see whether they're equal or not: the left hand limit and the right hand limit, and the function's value at that particular point, right? If these 3 terms are equal, if these 3 values are equal, then you can say that the function is continuous at that point x is equal to a. So I hope the idea of continuity is clear to everyone. Let's say you're drawing a plot of a function, and if you can draw it without lifting your pen, we're talking about 2D plot for now. If you can draw it without lifting your pen, then sort of that gives you an idea that it's a continuous function. There's no break. Okay, so that's the simple idea of visualization of a continuous function. So 3 things you will be checking. So what exactly this is? Where is the function? What is the function's value when you approach it from left hand side and you go towards the point x is equal to a? And the right hand limit tells you where is the function value going when you approach from right hand side. And this is precisely the function's value at that very point, f of a. So if the function is continuous, there is no break, these 3 values will be equal. That's your confirmation for the function's continuity at that point. Similarly, you can check for function's differentiability. So when is a function differentiable? Firstly, if a function is not continuous, it can never be differentiable, right? If the function's value is undefined at a particular point, you cannot say that the function is differentiable. It is, of course, not differentiable. But it may happen that the function is continuous, but it is not differentiable. That may happen. So again, to check whether a function is differentiable, it should be differentiable at all points. But you would be given a point where you should check the differentiability of the function. Now for that, what you should check? So again, the rule of thumb for a differentiable function is that the rate of change of the function should be same. If you approach it from left hand side or you approach it from the right hand side. So let's say this is a function, this straight line. Let's say this is a function which is an absolute function. Okay. F of x is equal to absolute of x. Okay. So if you talk, let's say this is x is equal to 0, and you approach this function from left hand side, go towards x is equal to 0, there's a different rate of change of function. Similarly, here there is a different rate of change of function. So this function is not differentiable at this very point. Similarly, if this function like this is a different rate of change of, and here there is a different rate of change of function. So this is another example of non-differentiable function. So here you have to check 2 things, the left hand limit and the right hand limit of this very thing. F of x minus f of a is a point where you're checking for differentiability, divided by x minus a. And similarly, right hand limit. So what exactly is this telling you? This is telling you the rate of the change of the function, right? F of x minus f of a, how much the function is changing, divided by x minus a with respect to the change in x. So these 2 things you will check for differentiability. If they're same, then the function is differentiable. Next topic that we are talking about is linear approximation. So the idea of linear approximation is, let's say you have some general function, some high order function, and you zoom in on this function enough that the line becomes sort of straight. Okay, that very straight line is what you're finding through linear approximation precisely. Okay, so let's say this is a function. Okay, and let's say this is the area that you're looking at. When you zoom in on this very point, let's say this point, this will become your precisely straight line. Okay, let's say this is equal to a, x is equal to a. So when you zoom in, this is actually not a straight line, but enough zooming in, it will be a straight line, and the straight line will be able to tell the function's value in the vicinity. Okay, and that straight line itself is what we are finding using linear approximation. So what is the beauty of this this very concept? So let's say you have a very let's say 10th degree function, and you can get a linear equation for that function, of course around the point A, not far away from that. Please note that, because linear approximation, you're trying to approximate the function's value using a linear equation, although the function was of higher degree. So as long as you are near that point A, you can use that linear equation. But if you are far away from that point, the error will be more, as in the difference between the actual value of the function and the approximated value will be higher. So linear approximation is always computed at a given point. So the point should be given to you. Now this is the formula that you should use to find the equation of linear approximation. L of x equal to f of a plus f dash of a multiplied by x minus a. A is the point at which you are finding the linear approximation. Now what all you need? You need the function's value at that point. You need the function's first order derivative at that point. All right. So okay, we'll talk about the expansion later on. So now what exactly is this? This is exactly the equation of a straight line at the point a comma f of a. Okay. So you know what is the equation of a line which passes through point x1 comma y1? That would be this: y minus y1 equal to m is the slope multiplied by x minus x1. It's the equation of the line which has slope m and passes through x1 comma y1. Now, when you replace x1 and y1 by a comma f of a, which is our point that we are considering, and the slope, of course, the rate of change of function at point a will be f dash of a. Okay. When you put in the values, this is what you get, which is precisely your linear approximation. Now, this was linear approximation, but you can also go for quadratic approximation, which is approximation of degree 2. Now, you might get a little better approximation. So as I said, as long as you are near point A, this linear approximation might work well. But if you go a little away from it, the difference will increase. But if you use a little higher order approximation, you might be able to do a little better. Okay, so it's up to you. So although linear approximations are generally sufficient and preferred given their simplicity, but you should also know how to go for quadratic and higher order approximations just in case you need. Now, what exactly is this? This is actually the Taylor's expansion of the function. So this was your linear approximation, and we are adding one more term, which is the quadratic term we are adding. And for that, we would need the second order derivative of the function at point A. This is just a pattern. I hope that pattern is clear to you. In general, you can get any higher order approximation using this expansion, which is again Taylor's expansion. So the pattern is f of a plus f dash of a multiplied by x minus a plus f double dash a divided by 2 factorial. This is factorial multiplied by x minus a square. So this is second order term that is added. Now next is third order term, where we have third derivative divided by 3 factorial multiplied by x minus a cube. And then we have fourth order term and so on. So wherever you want to stop, you can stop, and you will get a little better value of approximation as you add more terms to this, to your approximation. Okay. So,
excuse me, ma'am.
Any doubt? Yeah.
Yeah, I had a doubt in continuous. So in the graded assignment first question, there was a equation x square minus 1 divided by x minus 1. So,
okay.
So it was x square minus 1 by x minus 1. So the question was, is it continuous or discontinuous? It was told discontinuous at x equals to 1.
Okay.
But effectively, this is nothing but x plus 1, right?
See,
x square, yeah.
It's x plus 1 when you expand it, right?
Yeah.
But as it is, when you put x is equal to 1 over here, you get a division by 1.
In that way, we can write any function in this form, right, ma'am? Like any polynomial function is given, we can just multiply x minus 1 by x minus 1 and declare it as a discontinuous at x equals to 1.
Yeah, if there is x minus 1 in the denominator, the function will be not continuous, will be undefined, right? At x is equal to 1.
Yeah. Yeah, what I was trying to tell was, let's say if they had given f of x as x plus 5, then we can write x plus 5 as x plus 5 into x minus 1 by x minus 1. Again, it is discontinuous at x equals to 1. Like, what I'm trying to ask is, both are same, right, ma'am? If we plot this function, right? Yeah. So again, this will become discontinuous at x equals to.
If you plot this function at x is equal to 1, you will get undefined. You will get undefined at this point. Even if you plot this function, this will be continuous.
It's a straight line.
You
Yeah.
plot this one, try to zoom in on this x is equal to 1, you will get undefined there.
Okay, so let's say but like, I mean, I was thinking about the resultant equation, so it doesn't work like that, is it?
No, the thing is, let me add something. X minus 1 is cancelable only when x is not equal to 1. Okay.
Exactly. So that is what we do when you compute limits. So what do we mean by limit? So limit x approaches 1 plus, okay, or limit x approaches 1 minus. Now this is approaches 1 from left hand side, approaches 1 from right hand side, but not exactly 1. In order to get an approximated idea of what the value of the function will be, you do this expansion. When you do this expansion, you get x plus 1. Now let's say x is equal to 0.99. Now this is x approaches 1 minus, correct? Or x is equal to 1.01. This is x approaches 1 plus, okay? So when you put this value, by expansion, you get an idea of the function's value. That's why you do expansion only when you compute the limits, but not when you compute f of x. It's f of 1 when you're computing, you do not do this expansion because it's actually not defined at precisely 1 x is equal to 1.
Okay, so even though the resultant equation tells something else, we should always try to stick with the original, whatever they have given it. Even
whatever they have given, correct.
Just to find the nature, if you want, we can just expand and
just
find
to find the approximated value of limits. Now limits are not exact values, right? They are in the vicinity of x is equal to 1. In order to find those values, we do the expansion or L'Hopital's rule you would have heard of. They are used only in computing the limits, not computing the function's value.
Okay.
And
Thank you.
if you have plotted this, you can zoom in on the x is equal to 1 point and see that would actually be undefined.
Okay, thank you.
Okay. All right. So I hope you got you understood how to compute higher order approximation. So you see in this equation, this is actually a beautiful equation. Taylor's expansion. This is x is equal to a. You need everything at a local point. At point x is equal to a. What is that everything? Function's value at a, function's first derivative at a, function's second derivative at a, third, fourth derivative at a. You need all the local information and you get this equation of the function. This equation, which you can use to compute function's value at points which are not a, which are away from a. Of course, I'm telling you not to go far away from a, but you can a plus 1, a plus 2, a minus 1, a minus 2. They are, in the vicinity of a, and you can use this equation to get an idea of function value at different points. So this is precisely known as using local information to find global information. That's where Taylor series is used, and later in gradient descent also this will come back. Okay. So here, so far, the function was dependent on one variable, which was x. The function in real world, we get functions which are dependent on more variables. Let's say x and y is what f is dependent on. In that case, so when the function is dependent on more than one variables, in order to find its slope, we use partial derivatives, right? So dou f by dou x and dou f by dou y is what we compute to get the partial derivative. So accordingly, our equation will change for linear approximation. It will be f of a comma b. So a comma b is the point for this two variate function where we want to find the linear approximation. F of a comma b plus dou f by dou x at a comma b multiplied by x minus a plus dou f by dou y at a comma b multiplied by y minus b. So this is the equation of your linear approximation of a function depending on two variables. Next topic is directional derivatives, which means finding derivative in a particular direction. Now let's get back to the partial derivative that we just spoke about. dou I by dou x at x comma y is also represented like this. Okay. What exactly is this? It tells you the rate of change of the function with respect to x while keeping y constant. Okay, that's what it is. Similarly, the other component is dou I by dou y, which tells you the rate of change of function with respect to y when we keep x as constant. So we are keeping one direction as constant and we are finding the rate of change of function in the other direction. Now, if the function is dependent on two variables, we might be interested in knowing how the function is varying when we go a little in x direction and we go a little in the y direction. Okay, we might be interested in that, and that's where directional derivatives are used. So how do we convey how much to move in x direction and how much to move in y direction? For that, we need to give a direction vector. So precisely, directional derivative is rate of change of f if we allow both x and y to change in some direction u. This u is a unit vector in which direction we want to compute the function's rate of change. So directional derivative is nothing but weighted sum of partial derivatives itself. Okay, this grad f is the partial derivative vector, and this u is a unit vector. Please note this should be a unit vector. We are not interested in the magnitude, we are only interested in the direction. So it has to be first converted into a unit vector form if it is not in the given vector. So if the given vector is not a unit vector, please convert that first, and then you find the dot product with gradient vector. So you see this, this is u1. u1 is the first component of u2 is the second component. So it's a weighted sum of partial derivatives. That's what your directional derivative is. Okay, all right, any doubts? So far we have taken a good number of examples in solving the structure on directional derivatives and linear approximations. Please go through that if you have not done. Any doubts in whatever we discussed? Okay, there are some chat messages. I'm sorry, I'm not checked them. Take a look. Okay, solution of mock is not there on the portal, is it? I'm so sorry. I mean, I've actually shared it. Yeah, it should be there. I'll let me check this out just in a moment, and I'll get back to you here only. So sorry if it has not been uploaded. It was actually shared already. Okay, all right. Please speak up if you have any more doubts, else we can move on to week 3. All right, Abhinandan, maybe you can continue with week 3.
Thank you, ma'am. Yeah, okay. So week 3 consists of these following topics: 4 fundamental subspaces, orthogonal vectors and subspaces, projections, least square, and projections onto a subspace. Okay, so we'll revise all of those one by one. I think my screen is visible, right?
Yes, sir.
Yeah.
Okay. So first thing first, 4 fundamental subspaces. So a matrix basically consists of column space, row space, null space, and left null space. So column space is nothing but space expanded by all the columns of a given matrix. Okay, so here the columns are A1 to AM1, A12 up to AM2, A1n through AMN. Okay, so the space expanded by all those columns is called column space of A. So since you see there are m components in each column, we say the column space of A is a subspace of Rm. Okay, similar to that, we have row space. So row space is nothing but the space expanded by all the rows of a given matrix. So you can see all the row vectors consist of n components. Therefore, we say the row space of this particular matrix is a subspace of Rm. Similarly for null space and left null space. So what is null space? So null space is that subspace where we find x such that ax equal to 0. Okay, similarly left null space is comprises of all those vectors where A transpose x equal to 0. Okay, so these are the 4 fundamental subspaces, and these are used for different purposes like finding out rank, finding out whether the solution of a given matrix exists or not, and so many other cases. Okay, so let's now move to, any doubt in this? Four fundamental subspaces. Okay, then let's move ahead to orthogonal vectors and subspaces. So orthogonal vectors are basically those vectors which are at 90° to each other, or whose dot product is 0. Okay, those are the orthogonal vectors. Similarly, if there are subspaces such that the vectors present in each subspace are perpendicular to each other, then such subspaces will be called as orthogonal subspaces. So for instance, column space is orthogonal to null space, and row space is orthogonal to left null space. Okay, so the condition is mentioned here: two real vectors x and y are orthogonal if x transpose y equal to 0, that is dot product of x and y is 0, or y transpose x is again dot product of x and y. So these are all similar conditions. Okay, so similarly for your subspaces. So in subspaces, the only difference will be every vector in the subspace should be perpendicular to every vector in the other subspace. Okay. Any doubt in this? Okay, next important thing is, if you find the dimension of column space of A, then it gives the rank of the matrix A. Similarly, the dimension of row space of A will give the rank of the matrix again. The dimension of null space of A will give nullity. So there is a theorem called rank nullity theorem. So rank plus nullity will give me number of columns present in the given matrix. Similarly, the dimension of row space plus dimension of left null space will give me the number of rows present in a given matrix. So in this case, the number of rows in the given matrix are m, and the number of columns are in the given matrix is n. So suppose the rank of the matrix is r, then n plus, so the dimension of column space plus the nullity, that is, so the dimension of column space of A will be r, rank plus nullity n, that will give me the number of columns. Okay. Similarly, the dimension of left null space plus dimension of row space will give me the number of rows. Okay, so I think we can move ahead. Projection. So what basically is a projection? Anyone is having any doubt? I'm hearing some sound. Okay, so what are projections? So projections are nothing but basically what component of a given vector is present in the direction of other vector. That is nothing but the projection. So in this case, suppose we want to find out projection of B onto A. So that is given by this vector P. So P will be nothing but a particular part of A, or we can say P is equal to what to say, a multiple of A. So if you see this equation, then P equal to x hat A, where x hat is nothing but a scalar and A is the vector itself. So basically P is a scaled version of A. So how to find this x hat? X hat is found using A transpose B divided by A transpose A, which is nothing. So what is A transpose B? A transpose B is nothing but the dot product of A and B. And if you divide it using the self dot product of A, then you will get how much percentage of B is present in the direction of A. So that is the scalar x hat. And if you multiply it with A, you will get the projection of B onto A. Similarly, in case of matrix, now we have to just replace A with a matrix capital A, and B will be a vector. So you get into this formula. So projection equal to A transpose A whole inverse A transpose B. Okay, where this capital P is nothing but projection matrix, and it is given by A transpose A. One interesting property related to projections is that projection matrix is idempotent, that is B square equal to P, and P is also symmetric matrix. Any doubt in this?
Sir, one doubt actually. So, while creating that P matrix, right? So, sir would just want switch places between that the A that is outside and the B that was inside.
Okay.
So, how did that happen? Like, can we just switch in any place, or that was a bit confusing.
See, so to check this, better take an example. So if you take an example where you switch, I mean, if you take a matrix A, matrix A, not matrix A, some vector A, okay, let it be 1, 2, 3, okay, and then find A transpose A and multiply with some vector B, and do it using A transpose B divided by A transpose A into A. If you get same answer, it means switching is allowed.
Okay, sir.
Correct?
Okay.
So you can verify that way.
Okay.
Any other doubt? Okay, then we will move ahead. So next topic covered is least square approximation. So basically in least square approximation, what we do, suppose we have a situation where a system of equations represented by Ax equal to B has no solution. Okay, so this can happen due to various reasons. One prominent reason being there are too many equations, which means the number of variables that you want to calculate or find out is very, very less than the number of equations that you have. So you are having a lot of additional information than the number of variables that you want to solve. So in such cases, you won't find Ax equal to B has any solution. So what we do in such cases, we try to find out some technique through which we can find solution. Okay, so one such technique is least square approximation. Okay, so basically what you do in least square approximation, so from our prior knowledge, we know Ax equal to B has solutions if and only if B belongs to column space of A, right? So so if we have a system of equation where Ax equal to B has no solution, so to make it solvable, what we need to do, we need to project B to the column space of A. Then only this Ax equal to B will become solvable. So this method is called least square approximation. Got it? So again, when you do that, when you project B onto the column space of A, you get a projection of B onto column space of A. Now, so there will be definitely an error present in the equation that the model that you are finding out, okay, from the actual data. So that error is calculated using this error E equal to B minus Ax, where B represents the actual target variable which was given to you, and Ax is the projection of B onto the column space of A. Okay, so we try to minimize this error E using least square method. So what basically is the parameter? We try to find out square of deviations between the actual value present in B and the corresponding value that you get in projection, and then square it. So that particular thing is called squared residual, and then you sum it over. So basically we try to reduce the sum squared residuals to find the least square approximation of a given model. Okay, any doubt in this?
Can we do an example?
I cannot write, but I can give you an example for sure. So suppose you have a system of equation. Okay, some x1 plus x2 plus x3 equal to 3, x1 minus x2 plus 3x3 equal to 2, and x1 minus 3x2 plus 5x3 equal to 7. Okay, so your B, the B that you are getting is suppose 357. Okay, so that 357 is your real actual B, or the actual value of target variables. Okay, now suppose for this given B, the system of equation is not solvable. Then what is the thing that you will do? You will try to project B onto the column space of A. Now when you project the B into column space of A, now suppose you get a value 246. Fine. So the real values were 357 and now the projected values are 246. So what is the error? 3 minus 2, 1, 5 minus 4 minus 5, 1, and 6 minus 7, 1. Okay, all these are called residuals. Okay, now to find the total error, what you do 1 square plus 1 square plus 1 square. So this will give me sum squared residual. Now your aim is to reduce this sum square residual to as minimum as possible. So the model for which this sum squared residual is the least is called the least square approximation.
Okay. Okay. Thank you.
Got it? Anyone else having trouble? Okay, I think then we can move ahead if you have no. So you can see this x hat is the least square solution of norm or the length squared of b minus ax hat. So for which this particular value is minimum, we say this is the least square approximation of the given model. Okay, so we can have some solved problems for the cases. So first problem is find the fundamental subspaces of A. So basically, what you do while you find some fundamental subspaces, how will you find fundamental subspaces? So keep one thing in mind, whatever matrix is given to you, first reduce it to reduced row echelon form. I think you people can do that. You know how to reduce to row, this reduced row echelon form, right?
Yes, sir.
Okay. Then see, when you reduce the given matrix into reduced row echelon form, suppose my matrix was some 1, 2, 3, 3, 4, 5, 5, 6, 7. Okay, when you reduce into reduced row echelon form, suppose you get two non-zero rows and third row is completely zero. Got it? So you can say there are two pivots present in the given matrix in the row reduced echelon form. So for the first two columns, if you see, suppose the diagonal elements are 1, 1. What suppose it will be? Because you are reducing it to reduced row echelon form. So 1, 1. So first two columns has pivots and the third column value will be 0 since I am saying the third row is completely 0. So the columns corresponding to the first two columns of the row reduced echelon form will form the basis of column space of A. Got it? That is the method to find column space of A. Any doubt in this method?
Can you repeat?
Yeah. So first you have matrix.
Can you repeat?
Yeah, I am repeating. Step 1, get the matrix. Step 2, convert it into RREF. Okay. Third step is to see the corresponding columns for which pivots are present. So those particular columns will form the basis of column space of A. Any further doubt in finding the column space?
In reduced row echelon form, is it necessary that the pivot elements are one only?
Yes, I think the diagonal elements are 1, 0, right? Therefore, it is called reduced row echelon form.
Should be non-zero, right?
Yeah, it should be non-zero. Yeah, correct. So for those particular columns for which this pivots are present, corresponding to those in the real matrix, the original matrix that you give, form the basis of column space of A. Okay. Any doubt in the process?
Sir, in the matrix you have shown here for the 1, 4, 2, 2, 8, 4, minus 1, minus 4, minus 2. Here the
Yeah, I cannot hear you.
second row has 2, but it can be divided by 2. Did I?
Second row has 2.
Sir, like in the reduce in the R, second row has 2, so we can make it 1 as well, right? So will it be a
It's
pivot?
not second row, it's second column. Be clear with columns and rows. So in RREF, you are seeing 1, 2, minus 1, 0, 0, 0, 0, 0, 0. So rows are those 1, 2, minus 1 and rest 2, 0, 0, 0, 1. Columns are 1, 0, 0, 2, 0, 0, minus 1, 0, 0.
Yes, sir. So in the first RREF, we have got 142 in the first row, 020 in the second row. So in the so we can make it into 010, right? And
Yeah,
so
it's
the
not required.
pivots
So
will be one
yeah,
there and the one below that as well in the
yeah, so it is not required. Someone told that for RREF, the element should be non-zero, not necessarily one. Okay.
Yes, sir.
So can you compute this left null space? How you got this?
Yeah, okay, I'll compute, but I don't have any writing material with me. I'll tell you how to do that. Okay.
Yes, sir.
Okay. So see, for this particular example, if you see there is one pivot element in the first column and there is a pivot element in second column. So the column space of A will consist of corresponding columns in the original matrix A. Achha. So how to find the basis of row space of A? So all those non-zero rows in the RREF form the basis of row space of A. Okay. So if you see, so there are two methods of calculating the row space of A. One is either take the transpose of A and then do what you did to find the column space, or just find the RREF of A and then all those rows which are non-zero are automatically the basis of row space of A. Okay. Any doubt in this?
No, sir. Only left null space is an issue.
Okay. So for null space, again, you find all those AX equal to 0, then you get a particular solution of X. So all those, you will there only find the basis for the dimension of null space of A. For left null space of A, what you do the same process as null space of A, but with the transpose of A. So if you know how to calculate the null space of A, follow the same steps for A transpose.
Okay, sir.
Got it?
Sir, can you explain how to find row space with step-by-step explanation?
Actually, the issue is I cannot write. I don't have any writing material with me. Otherwise, I would have solved it.
Okay, sir, you don't write, but can you explain, please? Step
Which
by
space
step.
you want? Which particular space you want?
Row space, sir.
Row space. Okay. So row space has two methods. Okay. One method is you just transpose the given matrix A. Okay. So for given this particular given matrix, the transpose of A will be -1, 2, 1, then -4, 8, -4, and 2, 4, 2. Correct?
Okay, sir.
Now you do this RREF for this A transpose. Okay.
So directly, can we get the null space from the left null space from the null space?
No, we cannot get directly from null space.
Okay, sir.
Because it consists of transpose of A, right? So the vectors will be completely different.
Okay, sir. Thank
you. Okay. So the one who asked for row space, you got my point what to do?
Yes, sir. Yes.
Yeah, so that is one method. The second method is keep the matrix as it is, reduced it to row this RREF, and then whichever is the non-zero rows, they form the basis of row space. Got it?
So are we saying
Sir, last line.
Yeah, so the given matrix A, you find its RREF, whichever is the non-zero rows will form the basis of row space of A. Yeah, so someone was having any doubt.
Yeah, so I was asking, so we need not do transpose, you're saying, just keeping the A as is and then looking at the row.
Row in a sense, RREF may whichever is the non-zero rows.
Non-zero rows.
In RREF, not A. In RREF of A.
So then won't we get the same if I look at the for the column space also?
Yes, so no, we won't. So what you do in column space, you take corresponding columns from the original matrix.
Yes.
Or not. But in row space, you take the rows from the reduced matrix, not the original matrix.
Oh, okay.
So they will be different.
But sir, here it is taken in from the
Original matrix. Yeah.
What?
it is taken from the original matrix. It's because
Sir,
one
but
comes to original matrix.
142 is from the original matrix, no, sir?
Yeah. So for finding column space, you just need to find out which is the non-zero pivot and then take corresponding column from the original matrix. But in row, while finding the span of row space, you take the rows directly from the reduced matrix, not the original matrix.
But here it is given from original matrix.
So but here, yeah, so here so the span of rows which is given as 142, are you saying that has come from row reduced RREF?
It is not come, sir is saying that it should come from reduced row echelon form, but it is coming from the original matrix itself.
So what the method used here is A transpose, not what I am saying. So if you take A transpose, the vector that you will get will be different from what you will get from RREF. They won't be same.
So I think, sir, first I think to find the row space, we first transpose the original matrix, then we do the RREF, and that's how we get the span of row space, right?
That is one method.
Okay, good.
Okay, that is one method which is correct. I'm not saying it is wrong. The second method is take the original matrix, do its RREF, and take the non-zero rows.
Okay, got it.
So
Hello?
Sir,
Sir, I have one question here. So we take the transpose of the original matrix and do it. So we are referring to the original matrix. But when we are doing, we are not transposing the matrix. So we take it right from the reduced row echelon, whatever we are getting. So isn't it better to do the other way? Because I don't think both the things will be same. The span will. And
when
so
you are taking from the original matrix by doing RREF, you are getting the basis. Okay, so that basis and this basis will be same, just multiple of each other, some multiple.
Yes, sir. So, sir, it will be better to do the transpose because there we have the span from the original matrix itself, and when we are doing it directly
There is
from the,
no
we are finding.
Better in what sense?
We are referring to the original matrix.
So it's not like that. So in null space, you find nothing from original matrix. So is it bad? So see, basically you have to find the span of that given space, right? So there are different methods. Whichever is less complex for you, follow that. Got it? But you cannot say that particular method is better or this particular method is better because both are doing the same thing. Correct?
Sure. I have a quick query.
Yeah.
So in this, if you see by reduced echelon form, the first row we got 1. So basically the first row in the, while writing, we wrote row space of column space of A transpose is 142. Right, sir?
Okay.
And you told we can take directly from the first row of reduced echelon form as well, which is 1, 2, and -1.
Okay.
So both of them, will they span same thing?
give me a minute. I don't know for which they have calculated this 1 to minus 1. Is it for A
Okay, okay.
transpose or it's for A?
Okay, fine,
So
sir, fine,
that's
sir.
for A transpose.
Yeah,
Okay,
I
okay,
guess
my bad
it
then.
is for A transpose.
Okay, so what? So
A
basically, we
transpose,
can.
the first one is for A.
So basically, we can either take the reduced form row from the reduced echelon form or the corresponding pivot row from the main matrix itself, right, sir? Both of them will be same.
Yeah.
Because
So again, I'll repeat just to avoid confusion. Okay. For row space, I am talking about row space. There are two possible methods. First method is transpose the matrix and do what you are doing for column space. Okay. Clear with that?
Yes.
Yes, sir.
Yeah.
So
Second
this,
method, take the original matrix, find its RREF, take the non-zero rows.
So for example, now if we have two non-zero rows, then should we take both the rows?
No, it will always come same. It won't happen that A transpose may you will get something else and RREF may you'll get something else. Dimensions will remain same.
Okay, got it.
Okay. Achha, so better to avoid confusion, do this A transpose because I think you people are more acquainted with that.
so this result is for second method. It is solved by directly solving this matrix A.
Okay, so do that basically. If you want, if you know how to find the column space, just take A transpose, find its column space. That's it. Okay. Okay, right? No confusion. So Naveen Ghai, so what are free variables? Free variables are those for which we can assign a particular value. I mean, you can take any values and according to that, you find the values of the pivot variable. Free variables, you can take any value for them. Achha. Next is solution to Ax equal to B. This part is not important. So this basically tells you why we want B to belong to the column space of A. So the crux of the matter here is if you take the B such that it belongs to column space of A, then rank of matrix A and augmented matrix AB are same. Otherwise, they are different. Achha. How to find the projection matrix for A? I think you people have done enough of graded assignments to do this. So no, I don't think we will give any formula sheet. I think Anamika ma'am can tell this. But I don't think any formula sheet will be provided. And for sure, for the first 4 weeks, you don't require any formula sheet. There are no such requirement of that. Okay.
Sir, all these questions of numerical type.
Yeah, go ahead.
Is all questions of numerical type?
Regarding paper pattern and all, I think Anamika ma'am will answer if she is here. So maybe we can wait for some time. Okay. Okay, then next thing is least square method. So basically, you people have seen the tutorial, right? Any doubt in this method? I'll come to that directly if you have any doubt. Because basically you have to do this A transpose A, X hat A transpose B. So it's a formula based thing. I think we need not explain it.
So one question I had to find the error value.
And in last live session, we had.
Hello?
Yeah, go ahead.
Yeah, I had so once I find the best fit line, the error value which I need to find, So that I will find by substituting the values of A, right? I mean the X.
See,
in this line, I'll get the projection and then I will. Hello?
Yeah, you are audible. Go ahead.
Yeah, so what I was asking is to find that projection points onto the line. I will use this best fit line and substitute the points A, B, C, D, E there. And that will give me the actual points on the line, right?
See, what you will do now, in this particular case, you have got y equal to 0.7 x plus 0.7, right?
Yeah.
Now what you will do? You will do y hat 0.7 into 1 plus 0.7. So that is 1.7. So the first for the first case, b was 2 and from the mod 4 because x is 1, so 0.7 plus 0.7, which is 1.4. So from the model you are getting 1.4 and from the actual figure you got 2. So the error is 1.4 minus 2, which is 0.6, because you will take the absolute value. Okay. Now for the second data point, what you will do? Second data point is 2. So you will do 0.7 into 2 plus 0.7.
Right.
Got it? So it is 2.1.
Right.
And the real value is 1. So deviation is 1.1. Similarly for the third, 0.7 into 3, which is 2.1 plus 0.7, which is 2.8. So 3 minus 2.8, which is 0.2. For the fourth, 0.7 into 4 plus 0.7. So you are getting 3.5, which is 0.5. Next, for the fifth point, 0.7 into 5, which is 3.5 plus 0.7, which is 4.2, 4.2, and the real value is 4. So deviation is 4.2 minus 4, which is 0.2. Got it?
Yeah,
this
and
is the matrix.
And then when you square it, you will get the.
Yeah, so the square will be here 0.6 square plus 1.1 square plus 0.2 square plus 0.5 square plus 0.2 square. All this is sum squared residual. Okay?
Yeah, sure. Thanks.
Okay. Any other doubt? Yeah, error means the difference between the absolute values, Pranav. Error square is the squared error. But if I mean, it will be clearly mentioned in the question what you need to find out. So if there is a term squared error, then find the error, square it.
So this error is similar to the loss function, right?
So yeah, error is nothing but the loss. Loss of the individual data set, then you add up, you will get the loss.
Do we have to divide by the total number of variables? Like if there are 5?
Yeah, so that depends what they are asking. If they are saying find out mean squared error, then divide by the number of variables. If they are finding, they are telling you sum squared, then you need not divide. If they are saying root mean square, then you have to take the square root, then divide by the number. So depends what they are asking you to find out.
Okay, sir. Thank you. It's helpful.
Okay, so any doubt in week 3? Any further doubt?
Sir, can you solve the question of mock tests? Question number 14 of that slope and y-intercept slope is 0 and y-intercept is 2. I'm not getting that question.
Can you tell me the question?
I think that is 14th question mock.
14th question. Okay, I have to find it out. Give me a second, I'll find out.
Okay.
Whose doubt was this? I think I am not able to find that question. So I'll allow maybe to share your screen. Can you share your screen?
Wait.
I'll allow sharing screen. Okay, you share your screen.
Okay, okay, you allow.
Okay, 14. Consider a line with zero slope and y-intercept of 2. Okay, so zero slope and y-intercept of 2. By this, what you mean? The equation is y equal to 2. Okay.
Yes.
The sum squared residual obtained when the line is used to fit. Okay. So now what you need to do, see, these values are for the actual y's. Okay. And the model that you have is y equal to 2. So here form an extra column, error.
Okay.
So the first error will be 2 minus 2, 0. Next error will be 4 minus 2, which is 2. Then 1 minus 2, which is minus 1. And 3 minus 2, which is 1. This is the error that you are getting. Then form another column, square these errors. So here it will be 0 plus 2 ka square plus 1 ka square plus 1 ka square, which is 4 plus 1 plus 1, which is 6.
Yes. Okay, okay, okay. Sir, and this was, I was talking about number of free variables. What does it mean?
So number of free variable means when you are finding this RREF, okay? So in that you will get some pivot elements.
Pivot elements.
Apart from the pivot elements, whatever you get are the free variables. Matlab, if there are the order of the matrix is 3 and you are getting rank 2, then the third there is one free variable and 2 dependent variables.
Okay, 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 okay.
Got it? So for the free variable, you can put values to get dependent variable.
Okay, 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 okay. It's rank of null space will be free variable.
Yes, correct.
Okay. Thank you, sir.
Okay, so maybe if someone else wants to ask any doubt, sharing screen, I'll enable it. Otherwise, I'll disable. Okay, I'm disabling. Acha, so can we move to week 4 now? If we have no further doubt.
No, that, hello.
Yeah, go ahead.
That get 1 minute. Okay. Just I'll come back again later. I've forgotten that term.
Okay. Whenever it clicks you, just do come back. So we'll share maybe week 4 now and we'll talk about it. Okay, my screen is visible, right?
Yes, sir, it's visible.
Yes, sir.
Okay. Okay, so the first lecture is of linear and polynomial regression. So in revision session that I took for the previous run, I tried to explain features and records. So I think we have already covered that in week 1. So we need not repeat it, right? Or anyone wants repetition. So maybe I'll repeat. So suppose you want to find income of a particular person based on his age, education, qualification, and experience. So education qualification here is in the number of years. Okay. So suppose there is a person whose age is 35, who has done 15 years of education and has experience of 3 years, has an income of 100,000. Okay, similarly, you can read for other. So there is a person of 45 age and has 15 years of education and 8 years of experience, is earning 1,50,000. So similarly, for the third row, you can read out. Okay, so the income becomes the target variable and age, education, experience becomes the feature. So basically, what are the feature vectors? So feature vector for the first record is 35, 15, 3. Feature vector for the second record is 45, 15, 8. And feature vector for the third record is 35, 16, 5. And my target variable y is 100,000, 150,000, 200,000. Yeah, Srinivas.
Sir, if you could write, it would be a little more clear, sir.
Yeah, so actually, I'm really sorry for that. I don't have a Wacom access right now. Because I also prefer writing, but I'm not able to do that. I'm very sorry for that. So all these things actually I explained using by writing only, but this time I am not able to do that. Is it okay if I explain some?
Okay, sir, but last live session also we had this issue and it becomes very difficult for us.
Yes, sir. Actually, it's a little, when we write, it goes in that sequence and we are able to understand the steps. And this way, it is a little difficult, but then there is no option. So we'll have to just manage this way. Hopefully for the next session onwards, we won't have this problem, sir.
Yeah, I hope there is no such problem. So actually, I have this problem because I am not at my proper place right now where I used to be. So that is the issue that is with me. Maybe for other instructors, they are able to write, right? Or in other sessions also you are facing the same?
No, we'll continue now, sir. No, actually, madam also was writing, but we'll continue.
Yeah, so this is a particular case of mine. I am not able to write. For other instructors, they can write. So again, I apologize for the same. I'll try to explain whenever you have doubt.
Sir, it is okay. Actually, we saw the previous video of this session, and it is very helpful for us. If people are do want to get explanation, they can go back to the video and they can watch it.
Yeah. So I have explained this session, all
you can,
things.
Yeah. You can share the video link, like so that people will watch it again.
Okay, maybe if you can share that, it will be helpful.
Yeah, sure.
Okay. Okay. So again, so basically what you are doing, you have three features: age, education, and experience, and target variable income. So basically I was explaining how this x1 transpose theta comes. That sir has done x1 transpose theta, x2 transpose theta, x3 transpose theta, and so and so. So basically this is nothing but x1 is 35, 15, 3. So while writing in the form of feature matrix, what exactly has happened? We have to write this vector as a row form. Therefore, you take x1 transpose, not x1. Okay. Okay. Now, next thing, suppose after you form a model, you get the values of income as 100,100, then 149,000, then 201,000, and the real values are these 100,000, 150,000, and 200,000. So what is error? Basically, error you find out these small e1, e2, and e3 by subtracting the predicted values from the actual values. So in the first case, it will be 100,100 minus 100,000, so which is 100. Similarly, for E2, you will get this 149,000 minus 150,000. So you will get 10,000. For E3, you will get 1,000. Now you square it up and add. And suppose in the question they have asked you mean squared error. Then what you do 1/3 of this sum, that capital E. So you from that you get mean squared error. Okay. Next thing is when you get the data set, next thing is to form a model. So a model is nothing but features into some coefficients plus a constant term. So here it will be theta naught plus x1 theta 1 plus x2 theta 2 plus x3 theta 3. So this is a linear regression model that you are getting. So these theta is the matrix which gives you the value of parameters. Parameters are nothing but the coefficients plus the interceptor. Okay. Next thing is how to find the errors that I already told you. Actual value minus predicted value and square it. From that you get squared error. Next, the loss function. here is half into summation of the error squared or the sum squared residuals. So this half has no physical meaning as such. This is only done for a mathematical convenience that we'll talk when we move ahead. Okay. So in later steps, what happens? It becomes 2 into half and 2 gets cancelled and only this part remains. Achha. Next thing, when you write this, if you try to write this particular equation in the form of matrix, it will come up as capital E equal to half A theta minus Y transpose into A theta minus Y, where A theta gives me the predicted values and Y is the actual value. Now to find theta, what you do? See, in general, whenever we want to find the minimum or the maximum value of something, what we do? We differentiate and equate to 0. So in case of matrix, what happens? Instead of differentiation, we take grad, then grad of that particular matrix, grad E, and we equate it to 0. So from this, we get the minimum value of theta, the values of theta for which E is minimum. Okay, so if you solve it, del E equal to 0, you will get an equation like this: A transpose E theta minus Y equal to 0. And from this, you get theta equal to A transpose A inverse A transpose Y. Okay, so this detailed derivation I have done, and it is present in the discourse. A complete derivation, it is using pen only. Or in the previous session, I have explained this, so you can see that. This way is okay, right? I know it's not a substitute of actual writing, but it's okay, right?
Sir, why this E is equal to half of summation? Why, from where this half term comes?
So this half is just a constant. It has nothing, no physical meaning as such. So basically, what will happen? See, if you see this E equal to half A theta minus Y transpose A theta minus Y. So it is like square of A theta minus Y. So when you take del E, so when you differentiate X square, you get 2X, right?
Yeah.
So similarly, when you differentiate A theta minus Y transpose A theta minus Y, there will be a 2 multiplied. And this half is there, so this 2 and that 2 will get cancelled. So only for mathematical convenience it is taken. It has no physical significance as such.
Whether one consider or not, it will not affect this final result.
Yeah, final result is not affected.
Okay.
Okay, give me a minute. I'll try maybe something, whether I can write or not. Okay, I'll be able to write, but that will be a little slow if that is okay.
Yes, sir.
Okay, next thing is maximum likelihood. So what basically is maximum likelihood? See, now suppose I have been given a data points like this. Okay, and you have different models like this, and this. Now, can you tell me which of these for the given data points is the best model? I am telling this is line A, this is B, this is C.
The one which you drawn currently, right, in this corner, blue color.
Yeah, so
Or in the
if you see this diagram, you can very well say that A is the best fit model, right?
yes.
Yes.
Yeah. So if there is a new data point coming, so you can say this data point, the maximum likelihood of this data point on being A, or the likelihood of this data point on being A is maximum, correct?
Yes.
Yeah. So basically, now take the second method. What we generally do in least square, what happens? We try to find out a model such that this square or the deviation of the actual points from the model values is least erroneous, or the sum squared error is least, correct? So can we say that the likelihood of a point being on a model is similar to minimizing the least square error?
Yes.
We can say that, right? So that is what sir has explained in week 4 in maximum likelihood approximation. So there, if I am not wrong, so sir has used a very big formula, right? And that formula creates a lot of problems. So I'll try to explain that formula maybe. Yeah, so sir has used a formula which is product of root beta. Yeah, the log formula, that square root of beta 2 pi, then exponential minus beta 2, and so on.
Minus beta 2, yi minus x. Yeah.
Okay, so you basically get a equation which is like n by 2 log beta. So now n by 2 log beta, consider it to be A. Okay, why I'm saying it A? Because n by 2 log beta will be a constant, correct?
It's a constant. It doesn't have a theta term.
Yeah, then minus n by 2 log 2 pi.
Minus n by 2 log 2 pi minus beta.
Yes, minus beta and half yi minus theta I square. So basically, you have an equation like this: C equal to A minus B, correct? Okay. Now see, this B is nothing but the error function that you have read. L theta equal to half A theta minus Y transpose A theta minus Y, correct? Now, if you want C to be maximum, then your A should be this A minus B should be maximum, correct?
Yes, so B should be minimum.
So B should be minimum. So you can say maximum likelihood is equivalent to least square, correct? No doubt in this, right?
Yes.
So can you repeat this once again?
Yeah. So I'm saying the equation that sir has used has a form like this: C equal to A minus B. Okay. Now we want C to be maximum. That is, we are trying to find the maximum likelihood. So for C to be maximum, and since A is a constant, B should sum to be 5 equal to 10 minus x. So if my x will be minimum, or I can say 5 minus x, then if my x will be less, then equal to 5 is possible, correct?
Yeah, okay. Yeah.
Got it? Achha.
Yes, sir.
Next thing is polynomial regression, that is explained. So see, basically what happens, there are situations where a linear regression doesn't work. So for those particular cases, we use polynomial regression. So what exactly is polynomial regression? So what we do, suppose we have one feature, then we try to find out different combinations that we can have in a polynomial regression. So for instance, in a case we have one feature x1, then what are the possible combinations that we can have for x1? So it can be 1x1, then 1x1, x1 square, so and so, right? Different degrees of x1 are possible for one particular given feature. Similarly, for two features, what are the different combinations possible? 1 x1 x2, this forms the linear. Okay, then 1 x1 square x2 square, this forms a quadratic. Then 1 x1 x2 x1 square x2 square, all these forms the different combinations for two features. Okay, so what we do, first we do the transformation, that is we find different combination and then select the best possible combination that serves our purpose. And this is basically based on experience or the model that we require. Okay, are you getting me what I am saying? Yes, Srinivas.
Sir, can you explain with an example, sir? I'm not getting this point.
Yeah, okay. I'll explain with an example. Okay, now suppose I have a situation where I want to predict runs scored by a batsman based on the balls he has faced. Okay, so suppose he has faced 10 balls and 15 runs he scored. Then 8 balls and some 17 runs. So and so. Okay, now suppose I get a number of data points like this. Data points are spread like this. So if you form a line, so linear approximation is not a correct way of modeling this, right? So you have to go for some polynomial expression. Okay. Now for this particular case, we have one feature x1, which is the number of balls he has taken to get these runs. Okay, so what we will do now, we will try a model where only x1 is not present, but x1 is present and x1 square is also present. Or if it doesn't work, what we will do, we will go for x1, then x1 square and x1 cube, and then try to find out the model. Correct?
Sir, this step when a polynomial becomes a linear, that I'm not getting, sir. How is the polynomial being converted into a linear?
Yeah, wait. So the first step is to find out this transformation or do the polynomial transformation depending on requirement. Got it?
For 10 we will do this transformation. Which one we will do, sir? For 15 we will do what? We will do this transformation.
Yeah, wait. Suppose now the model that I considered first is something like this: 10 x1 plus 17. Okay, suppose this is the model I am getting, and this model is failing. This model is failing very badly. So I'll move to some other model. Correct? So now I am trying a model which is like this: 10 plus 1 x1 plus 2 x1 square. Now suppose this model works better than this. Okay.
Yes,
so
sir.
I'll go, yeah.
May continue.
Yeah. Okay.
Continue.
Okay. Now suppose there is another model that I am planning. Now what I'll do, I'll take x1 plus x1 square plus x1 cube, and in the preliminary analysis I find this model best works the best. Then I will try to model this model, right? From this model. So this is the part of polynomial transformation. So basically what you do, whichever feature you have, first you try to do its polynomial transformation. Okay. And then once you do the polynomial transformation, next step, you find out these coefficients. And finding out this coefficient is done through linear regression. Therefore, we say we are transforming polynomial into linear. Are you getting me? So this polynomial regression.
So when you say when you say you transform it into a polynomial, and we understand that the coefficient is what matters because the feature is going to remain the same. That's just that the order of degree is changing. But we know that the coefficients are the ones that are going to determine the entire model.
Yeah.
But how are we transforming first? So
yeah. So let me tell you, there are two steps involved. First, you try a linear model, and suppose it fails badly, and that you can check just by visualizing. If your points are not in the list spread all across the space, then you very well know that linear model will fail. So you have to try some non-linear model. Okay. Then comes second step. In second step, now suppose I have two features. Then what are different combinations that I can form using these two features? So you use, there are two features and you can have different combinations. What different combinations you can have? One, then x1, x2 you can take. Then you can take square of x1. You can take square of x2. Then you can take x1, x2. Correct? Only these transformations you can do, or any other transformation is possible?
No, sir, only these.
Only these, right? So what you'll do now, you will form the subsets, and according to that, you will try different models.
But here we are talking about two features, no, sir. In the previous three equations that you showed, everywhere it was x1. You just have a single feature, and the power is increasing. As in, you have a quadratic or a linear. I mean, that's the model that is changing. But here you have one extra feature itself. So that will definitely improve your.
Okay. So for that case also, let me take one x1, x1 square, okay, x1 cube, whatever. Okay. So what you do now for this particular case, now you can combine first two elements and try a model. Then combine second two elements, try a model. Combine last two and try a model. Combine first three, try a model. Combine all four, try a model. And you are not going to do that. Your computer is going to do that for you. Correct?
Okay.
So this is what you do. So out of all these 1, 2, 3, 4, 5, 6 combinations possible, you try every possible combination and form a linear model. You form a model, okay. Now, see, this transformation thing is in your hand. How you want to transform your given feature or features. Modeling you will be doing using linear regression.
Okay.
And therefore we say we are solving polynomial regression using linear method.
Okay, sir.
Got it? And this is trial and error actually. This is not like that. See, what you will do, you will form a loop. Yeah, you have done programming, right?
Yes.
Yeah. So what you'll do, you will give a whole data set. These 6 possible combinations are there. Now, for I equal to 1 से लेके whatever is the number of possible features that you can have, combinations you can have. Now try different models. Then try to check out the loss. So whichever model gives you the least loss is your answer.
Okay, got it.
Correct? So mathematically it may not be that easy, but while you do program it, it's very easy. And it is coming in machine learning techniques. Don't worry.
Okay. Okay, sir.
Okay?
Yes, sir.
Anyone else having any doubt? No doubts, right?
Can I ask on a previous topic? I actually missed that topic. Can I ask a doubt, or shall we ask it if it is the end? I'll ask.
Go ahead.
Okay. Actually, sir, when we were doing the null space and left null space, we have done that. No, so in that we have taken like we got in the example which you did just today, you got 2 rows which were zeros. So we have a null space which will have 2 different vectors.
Okay.
So in those vectors, when we are trying to decide the values, do we take the value of x2 and x3? Like we had 3 variables, x1, x2, x3. And since there is going to be one independent, two independent, one dependent variable, we have to fix the values of x2, x3 and find the value of x1.
Correct.
So now the standard form is that we take x2, x3 to be 0, 1 and 1, 0. Is it like that? Am I understanding it correctly?
See, that is one way of doing. Other way is take x2 equal to some value p, x3 equal to q, and then comma x1 equal to p into a vector plus q into a vector. Those two vectors are directly the basis.
Okay, okay. So that means it is not necessary that the values of x2 and x3 should be 0, 1, 1, 0. We can take, like, it could be some different multiple of that basic value.
Yeah, correct. So finally, you will, if you take any other value, you will get multiple of 1, 0, 0.
Yeah, that's it. Thank you, sir.
Yeah,
but if you take 0, 1 and 1, 0, that's okay. That's also fine. It's a
That's
simple, straightforward method.
practice that many people follow, but me personally, I don't follow that approach. I take x2 equal to s, x3 equal to t, and then
okay. No, but I think like this seems a little simpler, that we can just take 0, 1 and 1, 0, and then we can move forward. So that would also give us the correct answer.
Yeah. That method is also correct. But in while you take x2 equal to s and x3 equal to t, you get the answer directly.
Okay, sir.
No
Thank you, sir.
Yeah.
Thank you,
okay.
sir.
Next, we covered the polynomial regression, I guess. Next is regularization. So in regularization, what we do, basically, suppose we have two models here. Now, suppose we have two features, x1 and x2. Okay, not two features. So, okay. Now, suppose I have a data set, and for that I have two models, model A and model B. So, can you tell me, if I take 2 points on this model, these two models, x1 and x2, okay, so, and corresponding y1 and y2, I try to find out. So, which of these A and B will give me more changes or the wider changes? Any one of you? See, for this model A, corresponding to x1, there is a value y1, and corresponding to y2, there is a x2, there is a value y2 here. So the difference between y2 and y1, y2 minus y1 for A is way larger than the difference between this
y2 dash minus y1.
y1. So we can say A, the deviation that A is bringing is more than the deviation which B is bringing in our given outputs. So we can say A is more sensitive to changes than B. So in regularization, what we actually do, we try to reduce the slope of A so that this deviation is reduced. So basically we are trying from A to reach to B. This is what we do in case of regularization. So there are different kinds of regularization that we do. There is L1 regularization, L2 regularization, and there is a elastic regularization, which is a combination of both. So that you will study in detail in machine learning techniques. So for now, this thing should be clear. Okay. Next thing is why A transpose A plus lambda I is invertible even if A transpose A is not. Yeah, so I came to that only, Pranav. So suppose I have a matrix A transpose A, which is 1, 2, 3, 2, 5, 7, and 3, 7, 10. Okay, so now this matrix is suppose not, it is not invertible. Why it is not invertible? It is not invertible because due to some combination, one of the rows becomes 0. So its rank is not equal to 3, therefore it is not invertible. Now suppose by regularization, what you do, you add a term lambda I. So what will happen when you add a term lambda I? So lambda will be something, see, if this is my matrix and I am adding lambda I. So let me take the value of lambda as 2. So what I am doing, I am adding 2, 0, 0, 0, 2, 0, then 0, 0, 2. So what I am basically doing, I am adding 2 to the first element of row 1, then 2 to the second element of row 2, and 2 to the third element of row 3. So basically what is happening, there is addition of same term at different places in different rows. So what exactly is happening? All these rows are becoming independent. Since the rows are becoming independent, the rank will be now cannot be less than 3. Rank will be now 3 because all the rows have become independent. So therefore, the inverse is now possible. Anyone is having any issue in understanding this?
No, sir.
Got it, right? Okay. Next is eigenvalues and eigenvectors. So I think if you people have seen the tutorial, it may be clear with you, all of you. Or sir has also explained it using a differential equation method. So if you are having doubt, again in the last run, I took in week 4 in sessions, I have explained all the lectures. So after exam, you may go and see it.
One query, this lambda for regularization, when you said lambda I, that lambda is an eigenvalue?
No, this lambda is a scalar.
It can
This
be
lambda can be any scalar.
Any scalar, we just put it and add.
Yeah.
Okay.
Okay. So whenever you apply a linear transformation on some vector x, so and if you are getting ax equal to lambda x, then we say it is a eigen equation. Okay. Now in eigen equation, this x represents eigenvector and lambda represents eigenvalue. So basically what happens, we say for a given eigenvector, when we do linear transformation, then x only gets scaled. Its direction remains same. So that is when eigen equation is formed. So next, what is how to find the eigenvalues? To find eigenvalues, we take determinant of a minus lambda I equal to 0 and get lambdas or the eigenvalues. And to get eigenvectors, we use ax equal to lambda x, or we use a minus lambda I whole into x. This solve with instructor session also we did this. So by using this we get eigenvalues. Next lecture, I think diagonalization. Any doubt in this? These two? Dominant eigenvalues are the greatest eigenvalues. Okay, so if there are three the eigenvalues, 5, 3, and 1, then 5 is the most dominant, 3 is the second most dominant, and 1 is the least dominant.
It is the absolute value, right, sir?
Yeah. Then for diagonalization, we basically follow these steps. Step 1 is find eigenvalues of the given matrix. Okay. Now suppose we have lambda 1, lambda 2, lambda 3 as the eigenvalues. Next step is to find the eigenvectors. So eigenvectors, I think you people can find using a minus lambda into x. Suppose now these values are x1, x2, x3. Then find the matrix S. Matrix X is nothing but putting these values as column form, these vectors as column form. So you will form x1 column, x2 column, and x3 column in S. Then what you do, you just put S inverse AS equal to this capital lambda, where capital lambda will be lambda 1, 0, 0, 0, lambda 2, 0, and 0, 0, lambda 3. So this is the 4 steps that we do for diagonalization of a given matrix, which has distinct eigenvalues. Okay. Any doubt on this?
Is it always distinct?
Yeah, it should be distinct to find diagonalizable matrix. Otherwise, it is not diagonalizable. Since for diagonalization, what you require independent eigenvectors. So independent eigenvectors is possible only if your eigenvalues are distinct.
Okay.
Yeah, Srinivas.
So even if the eigenvalues are not distinct, if the eigenvectors are independent, then also we'll have diagonalization, right?
Correct. So, but the most important requirement is independent eigenvectors, and that is always true in case of distinct eigenvalues. And in cases where eigenvalues are repeated, in some cases, eigenvalue vectors can be independent, otherwise they are not independent, mostly. Okay. Okay, next thing is one important property is since we know S inverse A is equal to lambda for any diagonalizable matrix A. Now, if you multiply it 2 times, what you will get, this S inverse becomes I, then S inverse A, I, A, S, you get S inverse A square S equal to lambda square. So similarly, if you multiply it again with S inverse AS, you will get lambda cube and so and so. So basically, if you multiply this equation 1 k times, you get S inverse AKS equal to lambda k. So suppose you want to find out A raised to k, then you simply need to do lambda k. Now take this S inverse and S on right side and you will easily get your values. Since this lambda, capital lambda is a diagonal matrix, so finding lambda raised to k is not tough because you have to just raise those diagonal elements to the power k. Okay. Next, Fibonacci sequence has no that significance in terms of exam and all. Okay, so you can skip it if you want to. Then I think
Fibonacci, they explained, right? And sir had had a separate video for Fibonacci sequence. Is this like an added information, or will this kind of questions happen? Your voice is breaking.
See, it's a kind of particular application of diagonal. Hello.
Yeah.
Am I audible? Yeah. Okay. So there is some network issue at my side. Okay. So see, this Fibonacci sequence is a particular case of use of eigenvectors and eigenvalues. So, yeah.
So can we expect similar questions in
No. I don't think Fibonacci sequence will be having any weightage in the exam.
Okay, so they will not be giving any other sequence and ask us to solve this using it. They will not.
If you want to study it, it's just an application of diagonalization. That's it.
Yeah, we watched the lectures. I'm asking if some other sequence like this will be given in exam and they will ask us questions based on that, not Fibonacci.
So if someone asks that to you, the whole exam will take that question.
Okay, sir.
So lengthy questions, don't expect that. Yeah. I am also telling you the same thing. It is not feasible to ask.
Okay.
Next is orthogonally diagonalizable matrix. Diagonalizable is that you get a symmetric case. Your matrix is symmetric, so it is orthogonally diagonalizable. Okay. So whenever A is real symmetric, we get S inverse A is equal to capital lambda. And in this case, your S transpose S will be equal to I. So basically, the steps here is find the eigenvalues, then find the eigenvectors. Then this is the critical step. The step 3, which we do not do in case of normal diagonalization. Here, what we do, we normalize the eigenvectors. And then we do the same steps as diagonalization in case of orthogonally diagonalizable matrix. So for example, I have taken a matrix A equal to 1, 2, 0, 3. So since it is a diagonal matrix, we have eigenvalues lambda 1 equal to 1, lambda 2 equal to 3. Next, for lambda 1 equal to 1, we find eigenvector like this. So A minus lambda x equal to 0. So it is 1 minus 1, 2, 0, 3 minus 1. So I get 0, 0, 2, 2, x1, x2 equal to 0. Okay. Now, if I put try to find eigenvalues. I think one such question we did in last solve with instructor. We get the eigenvector of the form k0. So take the value of k equal to 1. So one of the given eigenvectors can be 1, 0. For lambda 2 equal to 3, okay, there is a audio lag, right?
Yes, sir.
Okay, so I think it may be better now. Okay, so for lambda 2 equal to 3, again we can find eigenvectors. So eigenvector here will be 1, 1. Okay, next step is to do S inverse AS. So how to find out S inverse? So for a given 2 cross 2 matrix, there is a simple technique by which we find S inverse. So suppose I have a 2 cross 2 matrix ABCD, then you do 1 upon AD minus BC, and then just interchange this principal diagonal DA, and then just give a minus sign to this elements, minus b minus c. So from that you get S inverse. Then put S inverse AS. So S inverse you have calculated, A you have, S you have. So your matrix will be like this. Okay. So I think this much is topics.
So sir, hello.
Yeah, go ahead.
Yeah, so for the right now, whatever example you showed was for diagonalization. Now, if you want to do orthogonal, whatever vector, eigenvector we got, we will do divided by norm and then take the S as.
Yeah, correct. So what you will do for this particular V1, you will do V1 ka normalization, which will be nothing but
1, 0.
Take this matrix 1, 0 and then divide it by its length.
Yeah, which is 1 itself.
1 itself. For V2, what you will do? You will do 1 upon root 2.
2. Yeah.
Correct? So that way you will do, but first check your matrix A should be symmetric. If A is not symmetric, don't do this. And how will you check a matrix is symmetric? You have to just check that apart from these terms, this should be equal to this should be equal to this, and this should be equal to this. Correct?
Yes, sir. Can you repeat that, sir?
Yeah, so suppose I have a matrix like this: 1, 2, 1, 3, 4, 2, and then suppose this is also 2. Then this 0, 5, 7. Now to check whether a given matrix is symmetric or not, this element should be equal to this element. This element should be equal to this element, and this element should be equal to this element. Basically, a symmetric matrix is nothing but a mirror image along the principal diagonal. Correct?
Yeah, A should be equal to A transpose.
Yeah, correct. A equal to A transpose, but yeah, so that takes a little bit of time by finding A transpose. Check this two, then this two, and this two, it reduces your time.
Okay, so only symmetric matrix we can find diagonalizations.
Orthogonally diagonalized.
Okay, orthogonal.
Diagonalization you can do for any matrix which has sufficient number of independent eigenvectors, but orthogonal diagonalization you can only do for symmetric matrices.
Okay, and what is the reason for that, sir?
Reason is derived by, I think, Professor Prashant in his lectures. So he has, so basically this S transpose equal to I is possible only in case of symmetric matrix. Otherwise, it doesn't hold good. So orthogonal diagonalization is therefore not possible.
Okay.
Okay. So can you please touch upon the eigenvectors of permutation matrix? Because up to my calculation, I thought it will be either 1 or -1, but I think it was mentioned as only 1 possible in all the cases.
In which?
Permutation matrix.
Achha, permutation matrix. Okay. So in permutation matrix, what happens? 1 and -1. These two are possible. So identity matrix is also a permutation matrix for your information.
Okay.
So all those matrix which has identity matrix and interchanged rows of identity matrix are permutation matrix. So if you take identity matrix, then 1 is also a eigenvalue.
So basically 1 is always an eigenvalue, -1 can be or cannot be.
Can be or cannot be. So -1 can be only if identity matrix you are not considering. If you are considering identity matrix, it will be all 1.
Okay.
Okay.
Thank you.
Sir, as far as I heard, permutation matrix was explained as the reverse, or you flip the identity matrix. That's when you get a.
Yeah. So
matrix,
If you
right?
go to the real definition of permutation matrix, identity matrices are also permutation matrices.
Okay. I mean, in the lectures it was not covered, so I'm asking if this.
Yes, sir. In lecture, it was basically told you get permutation matrix when you interchange the rows of identity matrix, and when that is the case, eigenvalues are always plus and minus 1. So that's why I got a bit confused at that part.
Okay.
It was 1 1 or 1 minus 1. That's what it is told, but they never said identity matrix is a permutation matrix.
Yeah, so identity matrix is also permutation matrix for all of your information. Okay, any other doubt? Okay, if we have no other doubts, so I think we can close session. Okay, how to find maximum rate of change? That is using directional derivative. Grad, if you remember the grad of f gives the maximum rate in that particular, and if you want to find the direction in which it is there, you have to multiply it with unit vector.
Sir, I had a question on projection matrix.
Yeah.
So, I mean, by looking at the projection matrix, I mean, do we get some insight like on?
Yeah, projection matrix of a given vector basically is you can say roughly is a space multiplying with that a particular vector gets into that space. So what is projection basically? Projection is nothing but taking component of a given vector in the direction of another given vector. So projection matrix basically taking that particular component out of the given vector. Okay.
Okay. Yeah. So I understand the projection matrix is basically like a transformation matrix where you input any vector, it will transform it to that space, that column space.
Correct. So suppose I have a vector B and there is a vector A. So when I am projecting B onto A, what exactly I am doing? I am taking an image of B on A. So basically I am taking an image of B in the direction of A. And therefore this image, let me call it P, is nothing but a scalar multiplication of A.
Right.
Correct. So what exactly projection matrix does? Projection matrix is basically acting as that particular scalar, which is transforming. Okay, let me take PB. Okay, KA, sorry, KA. So this P is basically doing what? It is converting, it is taking the component of B, this P. Okay. So projection matrix is basically helping you to find this component of B which is in the direction of A.
Okay. So for a projection matrix also you have rank and all those stuff?
Rank, it is a symmetric matrix, first thing.
Yeah.
Next, P square equal to P. So its equation, its characteristic equation is lambda square minus lambda equal to 0. So its eigenvalues will be lambda minus 1 equal to 0. So 0 and 1 are the eigenvalues. Okay.
Okay. So we had the mock questions, right? So can we expect same level of difficulty in the exam, or is it will it be slightly
little more difficult or little more easy, but around the mock?
Okay, sir. Thank you, sir.
Okay. And mostly, I guess, numerical questions will be covered with some theory questions here and there.
Okay, the mock had only a NAT question, so I thought it's going to be all numerical. There'll be theory questions also.
Anyways, these are very easy theory.
Okay, sir.
You have to just remember the crux. You will be answering everything.
I have a doubt in the graded assignment 4 actually. The first
Yeah.
question, if P is a projection matrix, then the eigenvalue corresponding to every non-zero vector orthogonal to the column space. Can you explain that? It answer is 0. I don't know how.
Yeah, okay. Now see project what exactly happens. So can you share your screen if I allow?
Yeah, 1 second.
Yeah, I have allowed screen sharing. I want to see that.
Okay. Do you able to see my screen?
No, I'm not able to see your screen.
Oh, it says you cannot. Somebody else is sharing. So.
Yeah, so I have stopped sharing. Yeah, go ahead.
Okay. Yeah. Yeah. The first question.
Okay. P is a projection matrix, then the eigenvalue corresponding to every non-zero vector orthogonal to column space of P. Okay.
I just want a graphical representation.
Graphical representation I won't be able to give you.
Okay, or just explain the question. Yeah, not able to. Clear, I didn't get a clear idea.
Yeah. So see, basically, column space of P will have all the solutions, right?
Yes.
Correct. So if there is a vector which is perpendicular to that, it means it is in null space.
Okay. Yeah. Yeah.
So for null space, the eigenvalue should be 0, right?
Okay. Okay. Yeah.
Right. So I think visualization is not required.
Okay. Okay. Thanks.
Yeah.
So the previous live session with Professor Arun had a visual representation. He actually brought some graphs and visualization, if that helps for this particular topic.
Okay. Okay. So you may check that. I have not seen that. So please go ahead and check.
Okay.
Okay. Then I think we are done. Or any other doubt? I'm there.
No, sir. We are good.
Okay. Then all the best, all of you, for your exam.
Thank you, sir, for the session.
Yeah.
Thank you.
Okay.
Thank you.
Thanks a lot. Thank you. Bye all.
Thank you, sir.